Okay, so yeah, continuing on our previous discussion, we were talking about how in reinforcement learning we need to take some exploratory movements in order to collect all kinds of information. And then over time we update our policy and we start taking exploitation movements that are the actions that the agent considers to be the best, and then it will take them in order to maximize the long-term sum of all the rewards. So in Q-learning, that is one of the most popular algorithms that is off-policy and model-free. We need to fill out this kind of table with all the Q values. So every state that we have, so by state we consider like state variables. We will have all possible actions that we can take under that state. And each of these actions for every state will have a specific Q value. And then over time, we want to fill out all this table with all the Q values of state and actions. And then the path of maximum Q values that we find will be the path of the optimal policy. And this is what we are trying to learn. So we do the action selection. At first, we use a probability of taking a random action. And then over time, we will just take better actions, also with a probability 1 minus epsilon. This is called the E-greedy policy, where the greedy actions are those we consider the best, and the others are just random. So here, depending on how big our epsilon parameter is, we are balancing how much exploration and how much exploitation we want to do. So initially, we want our epsilon parameter to be very high and close to 1. So we are taking exploratory movements all the time. And then as we are learning, we will decrease the exploratory parameter epsilon in order to start exploiting more the best actions. And then this is the equation that we use in order to make all these updates in this table, which is the equation that I showed earlier. So we have a learning rate, which will define how fast we want to make these updates. How fast? So if we use a very high learning rate, then it should be harder to get stuck into a local minimum because the step size is like higher. But then the updates will also happen really slowly, really fast, and this might lead to a lack of convergence of the equation that we will iterate in order to find all the Q values in this table. Then we have our discount factor. So as I mentioned earlier, the bigger our discount factor, we will be looking more ahead in the time horizon, trying to optimize the long-term sum of the rewards. And if our discount factor is close to 0, then we are focusing on optimizing only the immediate rewards, as all this term will be equal to 0. Yeah.
At the beginning, perhaps knowing the states is the easiest part, but how about the actions? I mean, how you choose the actions on your system?
Well, the action is, your control actions. You have to see what you are trying to control. And so then
you use several values for your control, and then you see what happens based on each action on each state.
Yeah. So for example, if you want to control an energy storage tank, then your action can be how much more energy you want to add to the storage, or how much energy you want to release from this. You want your action to be as closely related to your reward as possible.
And it should be discrete. And
well, we'll go to that, but for this approach, tabular Q-learning, we are working with discrete actions. So we will discretize all the actions, whatever they are, and then fill out this table. So there's a theorem that says that if you visit all the states and actions infinitely many times, then you will find the global optimum. So let's look at an example. What I was going to say. For example, if you want to control a storage device, then as I said, you want your actions to be as closely related to your reward. If your reward is energy consumption or energy cost, then, for example, the action being how much more energy you want to store or how much more energy you want to release is more closely related to the reward than if, for example, the action is a set point. Like saying, oh, I want this set point, then depending on where you are, if you set the set point at a different level, you might actually get more energy consumption or less energy consumption. So it might not be as good of an action. So it's important to choose the actions wisely. And then, we'll show this example. So this is just some example of Q-learning. So this is our agent and wants to reach the green box, which will give the agent a reward. And then if it reaches the red box, it will get a negative reward. And then these boxes are all the states, and then each of the triangles is an action that you can take. So taking this action will move the blue ball to the next square. So it just needs to find what are the optimal actions. So first it will start taking like random movements. So now it's seeing that this action has a negative Q value because it was here, took this action and got a negative reward. And then it's seeing that this one here is actually good. So it's updating it with a positive Q value. And then this action here make the blue ball the agent to advance into this state, which after that led it to this other state that made it get the reward. So it is also updating this action here positively in terms of Q values. So then it will continue to take all these different actions and move across the different states, and then it will create this mapping of what the Q values are. So in the end, the objective is to fill out all this table with the Q values, and then when you are only exploiting the right actions, when you are in a given state, you will always take the action with the maximum Q value. So if we are in this state here, then the action with the maximum Q value will be this one that has 0.8. So you will always take that action that will lead it to this other state. And then in this other state, this one has the highest Q value that will move the agent to the box in which it will obtain the reward. So then if we iterate infinitely many times, we can find all the Q values. And then we have also the state values, which are the equation that I showed before. That was the V, which is the value of every state. So the Q values are the values of every action in every state. And then the V values are the values of the state itself, like how good or bad is it being in a given state. So what do you think it might be the problem with this kind of Q-learning that is tabular?
Trying to compute the matrix.
Because you need to visit infinitely many states and actions, So the main problem here is that it was also answering Ali's question, that is for discrete states and actions, right? So depending on your system, it might not be well suited for your problem. And
So if you have a continuous action, like variable that you can control that is continuous, then you discretize that? That's how you do it, or? Well,
that's one option. So one option would be to discretize your action, and then there's another option that I will show now. So the first one is to find the course of dimensionality. The course of dimensionality is a basic problem, which if we have discrete states and actions, as we continue to add more states and actions, then the total number of possible options increases exponentially. So to solve this problem, we just use an artificial neural network. So we find our Q values with the equation that I showed earlier, and then as inputs into the neural network, we will use the states and the actions, and we will train it using the Q values as targets. So our neural network is going to learn how this table looks like, but it's also going to generalize. It's going to learn the Q values of state and actions that we have never taken by estimating them and interpolating. So the equation that I showed first, it was a bit different. It had a learning rate. So when we use a neural network, this learning rate, we turn it into 0, because in reality, we are using the learning rate of the neural network itself to perform the updates. So then the equation will look like this. And what we will update and what we will adjust will be the learning rate of the neural network in order to learn. Yeah, so the bigger our learning rate, the faster it will learn, but it will be harder to converge, although it's easier to avoid getting stuck in a local minimum. And then if we use a smaller learning rate, it will take many more iterations to learn, but then it will also be more stable.
So what it means is that the QSNA is updated by the neural network. So you send all these states and actions to your network as an input, and then in the output you have this.
Yeah. Yeah. So what happens here is that we're trying to update this, right?
Mm.
But we need to find what the maximum Q value is, which is the Q value of the optimal action. So in order to find it, so this is this S prime and A prime are the next state that we are seeing. So what we need to do is to take the state in which we moved on, and then we will input that state into the neural network. And then we will try all the possible actions that we have here. So we still need to try all the possible combination of actions for the state we just moved in. And then obtain all the possible Q values for every action in the state we are in, and then make the update with the maximum Q value that we find, if that makes sense. Yeah. So again, the state we are in, all the possible actions, get all the possible Q values for those actions, and then make the update. So yeah, so still if we have many actions, this problem might be untrackable, which is a problem. So then what we can do so if our problem is relatively simple and we don't have many actions, this is probably a good option. It's probably more stable. We can just discreticize our actions and use this. It's called DQN. But for continuous tasks, when we can have infinitely many actions, then we want to use an actor-critic method, which is in which we have a second neural network. So we have the critic network, which is the same one that I showed earlier. It will just map the state and actions with the Q values. And then we have the actor network, which takes the state we are in, and it will return the optimal action. So the actor network is actually the policy that we are trying to estimate. So then we have this equation, right, that is being mapped by the critic network. So the problem that we had is estimating these actions, because we had to input all the possible actions for a given state into the critic network to find all the possible Q values and then find the maximum one to make the update. But now we have the actor network, which gives us the optimal action for a given state. So what we can just do is to take the action of the actor network for a given state, and then we input this state and this action into the critic network, obtain this Q value, and then use it for the update. And then with this new Q value, we go to the critic network and we update the critic network by retraining. So we can update both networks one with each other. So then the actor network is trying to find the optimal actions. So then we have the environment and we need to take actions to try to solve our problem. We can either take this action or a random action, or another option is adding some exploratory noise to this action. And then we just take this action into the environment. We will do this more in exploration. When we want to exploit the optimal actions, we can just take only deterministic actions, or we can reduce this exploratory noise to 0. Then we take these actions here. Then we obtain a tuple, or a set of the next state. We have the state, the action that we took, the reward that we obtained from the environment after taking this action under this state, and then we obtain the next state. So then we can store all these tuples into a large batch or a buffer, and then we can replay all this information and iterate in order to find the targets. So in this equation, this is just the Q update. So this Y value is the target, which is actually the Q value. And then we will use this Q value in order to make the update of the critic network. So here we just try to minimize the error between the predictions of the Q values by the critic network and the targets, which are the updated Q values. So we will update the parameters of our neural network in order to minimize this loss. This loss, well, it can be the mean square root of this, for example.
Sorry, I'm trying to understand what the rule of actor network is. So instead of exploring all the possible actions, you choose one best action there, right? Based on the states. And then use that in order to train your critic network after the loop.
Well, I mean, so there are two things here. So one thing is the actions that you are taking, and another thing is the actions that you are going to use to make this update, which are different. So for this update, so here you have this function that is just trying to estimate what the Q values are for all the possible state and actions. So then to make this update, you will just try all the possible actions into this network. It's not that you are taking these actions into the environment. You just take this neural network, get this state, input all the possible actions into the network, not the environment, and find the Q values and make the update. The advantage of the critic is that you don't need to try all the possible combinations of actions into the neural network. You know, in none of these cases, you need to take all possible actions into the environment. It's more about how many updates you need to do in this neural network. Let's imagine you can control like 5 storage devices, and you discretize each storage device into 10. Then you will have 10 to the power of 5 possible combinations of actions that you will need to test into this neural network to find all the Q values and then find the maximum one. So instead of discretizing that and doing all of that, you just try to estimate that 5-dimensional action with this actor network. Then you can just input the state you are in. It will give you what combination of 5-dimensional actions is the best one. And then you can input that into the critic network and obtain the Q value to make this update here. Then you update the Q value, obtain the target, and then you minimize the loss between the target, which is the new Q value that you found, and the Q value that the critic network is predicting. And you minimize the loss, and by minimizing this loss, you can update the parameters of the neural network. And then the trickier part is how we update the actor network. So for the actor network, we want to find where are the actions that maximize our Q values. So we will use the gradient of the Q values with respect to the actions. So yeah, we take the gradient of these Q values and the parameters of our neural network with respect to the actions, and then we backpropagate that to update our network. So this, over the paper, looks overly complicated. Like if we wanted to code this, it could be difficult, but then in practice, using all these Python packages is actually very simple to make this kind of update. We don't really need to take all these derivatives. So long story short, we will have the environment and the agent taking actions over it. And then in order to address the problem, of course, of dimensionality, we will use a critic and an actor network. The critic network is evaluating how good an action is given a certain state. And then the actor is just trying to estimate what is the optimal action given a certain state. And then the updates of these two networks are intertwined with each other, and we will update them until we find convergence. So the most simple actor-critic method that we have is called deep deterministic policy gradient, DDPG, but then there are many other actor-critic methods or algorithms that we have. So these are some model-free state-of-the-art algorithms that we have. The deep deterministic policy gradient, or DDPG, is essentially what I showed before. It's pretty much the same. And then we have an improved version of it, which is TD3, or temporal delayed update or something like that, which is an updated version. So these two methods are a bit noisy because we have so many neural networks and we are making all these updates, and the update of one network is related to the update of the other. Then when we have some errors in these updates, they might propagate, and they might be, they can add a lot of noise into the system. And then there's another method, which is of Actor-Critic method, that we will be exploring further tomorrow, which is more stable, and it shows pretty good performance. And on the on-policy methods, we have the proximal policy optimization, or PPO, which is it's also really good, but as I mentioned earlier, it's a non-policy method, so it cannot really learn from historical data, and it's not as sample efficient as the off-policy methods. So it can work very well as long as we have some kind of a simulated model that we can train it again and again. But if we want to learn in real time or from historical data, since it's not very sample efficient, then we would need to take so many actions over time in order to learn. So we want to typically avoid on-policy methods for real implementation and try to focus more on off-policy methods that can make use of historical data and that are more sample efficient. So right now I focus a lot on the interaction between the agent and the environment. And now I want to discuss a bit more about the environment itself. So typically in reinforcement learning, it's relatively complex to write your own agent or to write your own reinforcement learning algorithm. But there are many algorithms already uploaded that you can download from GitHub and easily test them. So if you have a problem that you need to solve, it can be relatively simpler to develop your own environment that is compatible with reinforcement learning controllers that are already developed and that have been tested by the computer science community. And this is very important also for reproducibility of the results and the standardization of the research. So when I showed earlier that has been an explosion of research in reinforcement learning applied for demand response and for energy systems, I also realized that it's really hard to compare the algorithms with each other or to know how good they are. So typically, people will test the reinforcement learning agents and then they say they are really good compared to some other controller that they have. But it's really hard to know if that's actually a good controller or not. Like maybe the controller they are comparing it with is not great to start with. So maybe the reinforcement learning controller is doing great because of that. And then if someone else comes with another state-of-the-art reinforcement learning algorithm, if they test it in a different environment, we cannot really compare the results of one person with the other because they might be controlling different things. So in the computer science community, they use OpenAI environments that are already standard environments, so they can all test the reinforcement learning controllers into the same environments and then see how the performance metrics look like. And then it's really easy to know which algorithms are working better. So here are some of these environments that we have. So they have physical properties and they all have some objective that we need to accomplish. And then we can test different reinforcement learning agents on these environments and then see how fast they converge to a solution. And what is the average reward, for example. And this is part of standardization of the research. So here, for example, in this paper, they are comparing the soft Actor-Critic with the DDPG, PPO, and different algorithms. So they test it on many different environments and then see which ones are performing better in each of them. You will always see in reinforcement learning research that, so this is the cumulative sum of the rewards. So we want to maximize this. So you will typically see that there's some band around the results, like uncertainty band. This is because since we are using neural networks, depending on how we initialize the parameters of our controller, even if we test the same agent on the same environment, this initialization will change the results. So yeah, some controllers might perform really well in some situations, and then you run it again and it performs poorly, which is a problem of stability. For example, like this purple controller here, it has a band that is like really large. So in some cases, it's doing like probably better than any other controller, but in the worst cases, it's not doing so great. So there's a very large uncertainty band that we need to account for. So yeah, when doing research in this topic, we typically want to run our controller for many different types of initializations. Maybe we run it 20 or 30 times, and then we plot this kind of band to see how it's doing in different situations and see how robust the controller is. So yeah, I will show how one of these controllers looks like. So this is the inverted pendulum problem. So here the soft actor-critic reinforcement learning agent is trying to stabilize this pendulum just up here. So yeah, it might take a few minutes, I'm not sure. But it will basically start taking random actions, and then whenever the pendulum reaches a vertical line here, the agent will receive a reward. So then, yeah, over time it's trying to see, it can take continuous actions, and then it's also observing different states from the environment. So yeah, over time it doesn't know anything about the environment. We could implement this here into a building or anything. It doesn't really matter. But yeah, over time it will just try to learn from this environment through interaction with it, and just try what the optimal actions are. Yeah, it might take a few more episodes or states. Yeah, so here we can see all the states, all the steps that it's taking. So in every step, it's taking one action and observing one state. And then we have the episode. So we define each episode typically for a certain number of time steps. And yeah, for a certain number of time steps. So for example, let's say we want to control a building for 1 year. Then our episode will be 1 year, and our time step will be the time resolution, which can be 1 hour, if we are taking actions in 1 hour period. And what we do is that we run the same building again and again for a period of 1 year, taking different actions every hour, and seeing all the rewards and making all the updates. And yeah, and then just seeing how just plotting all these cumulative rewards for all the episodes. So yeah, I think pretty much it's almost there. Oh, got it. Can we stop this? So yeah, in order to standardize this research, what we've done is to develop CityLearn, which is an OpenAI gym environment for demand response, in which we have a microgrid with many different buildings, typically 9. And then each building will have some storage devices for cooling energy and for domestic hot water. And then they are all fed by heat pumps that will take electricity from the grid, and with a given coefficient of performance, they will provide cooling energy into the water tank. And then this efficiency of the heat pump will depend on the weather conditions. So when providing cooling energy, the colder it is outside, the higher the efficiency of the heat pump. So it can provide more cooling energy using less electricity. And then regarding the hot water, we have just electric heaters with a given efficiency that they will provide this hot water. Then some of the buildings might have a photovoltaic generation, and then they are all connected to the same feeder. So the objective is to minimize the peak energy consumption over the whole year, and then minimizing the average monthly peaks, maximizing the load factor, minimizing the net electricity consumption from the grid. So basically trying to flatten and smoothen the curve of demand in the district. And then the environment is built in such a way that it is relatively easy to implement either a centralized controller that controls all the buildings. So if you have 9 buildings, you might have about 15 possible actions. Some buildings, typically the actions will be adding more or less energy to the storage device, and each building might have 1 or 2 storage devices. They all have cooling storage, and some of them have domestic hot water storage as well. Then all the heating and cooling loads for the buildings have been pre-computed in a simulated environment. They are always, the supply devices will always satisfy the energy demand of each building. So this heat pump and electric heater, they are sized in such a way that they can always supply the energy that the buildings require. So what we want to control is the storage in each building in order to flatten just the electricity consumption here. So the objective would be to develop a stable plug-and-play controller that we can implement either in each building in a decentralized way or in all the buildings in a centralized way, and that can do this kind of load shaping. So we have in the environment 4 different climates, and then in each climate we have a district with these 9 buildings. So you can test it in any of these different climates. For tomorrow you can go to citylearn.net, which is the website of a challenge that we are proposing, and you can download the environment from the GitHub, and then install these packages and make sure that it's working. For some things it will require TensorFlow, also might require PyTorch, and then we will be using the OpenAI stable baselines, which are reinforcement learning algorithms that are already on the internet and that we can easily implement for reinforcement learning use. So you can try running the example baselines and see if it gives you any error. And if there's any error because maybe you don't have some of the packages that are required, then you can install it. So this is how the environment looks like. It has some files in the data in 4 different climatic zones. Each of these files contains the energy consumption of every building, and then there is a JSON file with the building attributes for every climate. So each of these buildings will have a different building type, and then also a solar capacity installed in kilowatts, and also the heat pump, the electric heater, and then the chill water storage. They'll have different efficiencies. The heat pump will also have different features depending on the building. So in the building attributes file, you can see these features that we don't really need to change. And we have 4 different climate zones, each of them with 9 buildings and its associated files. There's a file that contains the solar generation for 1 kilowatt of power installed. So if your building has 100 kilowatts, then it will just multiply that 100 by whatever there is in this file. And then there's also weather data that the environment will be using as states. So the weather data is not only present data, but also predictions of data in the future. So here's the CityLearn class. If you are curious and want to see how everything is coded inside. And then it's reading things from the energy models file that contains class models from the buildings, the heat pumps, the storage devices, and everything. Then we have a file that is an example RBC, or rule-based controller, in which we run this. We first run the system with 9 different buildings for no storage, and then we run it with the storage and with a rule-based controller, and see how it performs. So here, we can see the blue line is without solar generation, the orange line is with solar generation, and the green one is with adding storage and a rule-based controller. So we can use a reinforcement learning agent and then plot something similar. And then all the results that we obtain will be normalized by the results of the rule-based controller. So if you are obtaining results that are greater than 1, it means you are doing worse than the rule-based controller, and lower than 1 means you are doing better than the rule-based controller. The rule-based controller has been manually optimized to try to obtain already good results and reduce the peaks of electricity and flatten the curve of demand. So if your reinforcement learning agent is able to do better than that, is already a good thing. Then we have the reward function, which is here already defined. So here I have defined the reward functions as a quadratic function, so of the energy consumption. So basically, by defining the reward as a quadratic, the quadratic term of the energy consumption, you will just try to flatten it as much as possible. But yeah, you can also change this, and if you want, and then write your own reward functions, if you are going to use it like either tomorrow or in the future for any kind of research. Yeah, and then this is the most important file probably, where you can define all the states and actions of each building.
Just one question, because I already asked everyone to download the CityLearn from the GitHub, but I think some of the codes have been changed in the last couple
I made an update like 1 or 2 days ago.
So
you
we have to download from the GitHub.
And then
Also,
then with a new update, it might be using TensorFlow for one of the
And I think the version of TensorFlow, again, that becomes important for Windows.
Yeah, so I think it's at least so no later than 1.14.0, but I think if it's 1.13 or something like that, I think it should be fine. So
and also the Jupyter Lab, I think you have to install that on Conda as well.
Yeah, so if you open this on Jupyter Notebook, it might not work properly, so you need to open it with Jupyter Lab instead. Yeah, so you can try to run this model of Actor-Critic. So this is taken from the OpenAI baselines. So you can just run this and see if it's working. This is... Well, you can Google OpenAI stable baselines, and then you have many different algorithms that you can implement. Yeah, this one, stable baselines. So yeah, here there are many algorithms, and showing we have implemented this one, the soft Actor-Critic. So yeah, there is an here is showing all the parameters that you can update. Stable baseline soft Actor-Critic, and then here's an example on how to implement it, which is really short. So here is creating an OpenAI gym environment. So we will replace this by CityLearn, this line here, and then we want to implement this model, the SAC.
So, Jose, I think it would be good if you go back to your last slide. You know, we have a couple of minutes, so maybe everybody tries to
makes sense.
Do this and get this to work. You know, running that Jupyter notebook or lab. So at least we know that we are ready for tomorrow. So
Exactly.
it will be a good exercise now.
Yeah, so I think I have all the ones you need here, but yeah, just in case, I'm just telling you to run it just to make sure. So if it doesn't run, you can download whatever you need. Oh yeah, so yeah, I'll show it. Yeah, so if you have Anaconda prompt, you can open this and run it as administrator. So then you want to go to whatever your repository is, in this case, wherever you have CityLearn. Yeah, and then go to the repository, and then you just run Jupyter Lab, like this. And then you run it, and it will either open a window in your Chrome browser, or it will return you this address that you can just copy. And then you can just go to your browser, paste it, and it will open Jupyter Lab for that notebook, yeah. And then to install any of the packages, you can use either conda install, or you can use, in many cases, just pip install, and then whatever you package that you want to install. If you want to reinstall TensorFlow, you can just do uninstall yeah, TensorFlow, and then I think it was, and then the name of the version, like 1.15. This, you uninstall it, and then you can just install the other version. Yeah.
So I can see this example base case in my Jupyter lab.
The example base case.
Yeah.
baseline?
Your
Do you download the last?
So you said run the example base case in Jupyter lab.
Baselines? Yeah.
Here, but I don't see it. It's central.
Oh, I think it. Oh, sorry. I think I changed the name. I think it's a central agent.
Oh, okay. So maybe.
My bad. Yeah. So sorry about that. Yeah. Example. Yeah. I think it's sorry. Yeah. I think it's this. This is the name of the file. Example central agent. I believe. Yeah. So GitHub. I think it's this one.
Same problem too,
Eh?
yeah. We don't have a module called stable baselines. Yeah, that one. We don't have a module called stable.
Yeah. So so that's my bad. It's called a example central agent. My bad.
No,
The-
I'm actually opening.
It says.
Yeah. So your line 3 there, errors up.
Hmm?
So your line 3 says from stable baseline SAC policies. That one errors.
Oh, gives an error.
You can't find that module stable baselines.
Yeah.
Okay.
I don't see that as a file anywhere in your folder at all.
No, you need to install this
Oh, is it a package? Is it?
as a package. Yeah.
Oh, sorry.
What is that package?
Stable baselines.
Yeah. So you can go Google OpenAI stable baselines, and then it will tell you how to install it. Let me see. Installation. Yeah. So I think stable release. Yeah, I think it's this one. Pip install stable baselines.
So it's not. It's better to put it in your slide because it doesn't say in the requirements.
Yeah, here. OpenAI stable. Oh, yeah, like literally the name. Yeah.